When you hear the term AI, what comes to mind? I think for a lot of people, we would nowadays think of tools like ChatGPT to help write emails, summarize documents, or even generate some code. But for engineers, there's actually a different application of AI that matters just as much, if not more. And that's one that doesn't focus on interpreting human language, but instead focuses on learning the language that machines use to speak to us. And how do industrial machines and systems speak? It's not in English or French or Italian, it's in numbers through sensors. We can get information on pressure, temperature, flow, speed, power. And when you're trying to monitor, optimize, or control equipment, this is the language that you need to understand to know how to monitor, optimize, and control your equipment. So whether you're operating a Formula One car, a drilling rig, a processing plant, or a factory floor, your equipment is always streaming data when it's online, and that can be from a large number of sensors. You could be dealing with 300 sensors on a race car to 5,000 sensors across an oil field, and this data arrives as a continuous feed, as time series data, where there's numerical values being recorded over time. And this data from these sensors alone, it's helpful, but it doesn't do us any good if it's just sitting in a database. It needs to be actually processed, interpreted, and understood, and ultimately applied. And that's where signal processing comes in. And this is ultimately the transformation of sensor data into insights, patterns, and really decisions that we can make. And this can be done manually by a person, by an engineer, or it could be automated using different types of algorithms. And no matter the industry, the principle is the same, that the decisions we make based on this interpretation directly impact the performance, efficiency, and reliability of our system. It impacts how much gas is sold, how much ore is recovered, or how stable your hybrid engine runs over a race event. And AI really helps change the equation, not by removing engineers from this process, by helping them work faster and smarter with data and at a higher scale. So the way that I like to think about it is, imagine you're trying to listen to 10 people talking at once. It would be hard, it would be fast, loud, and there'd be a lot of overlapping information. And this is what it's like when modern equipment streams real-time telemetry data to engineers today. Even the best engineers are going to have limits, and there's only so much data that you can process at once before, like anyone, you would miss something important. And the goals haven't changed. We are trying to drive uptime, we're trying to drive output, we're trying to drive efficiency and reliability. So how do we do this today when there's more data than ever? Well, we need modern tools that help engineers stay ahead, not get buried in noise from different flags and alerts, and tools that really provide us with enhanced signal processing capabilities. And the good news is that if you can look back over past performance and you know what good and bad looks like, if you could point to the patterns that lead to success or failure, then you might already have what you need to train AI and machine learning models. To apply AI and machine learning to time series data to detect patterns, classify events, and even predict how things will respond to change, so that you can start to think about how you can apply that to the decisions that you have to make. And this really is a game-changing application of AI, because you can now use your real-world data that you already collect to then start providing you with guidance on the next step, the next decision that you can make. And you don't really need to reinvent your operation. You can really start small, assess which AI projects are most relevant to your operational challenges and priorities, and really implement individual applications that focus on solving specific challenges one at a time. And so when we work on these kind of projects, when we're delivering solutions, we typically use supervised machine learning, which is where we're defining specific target variables that we want to get a model to estimate or predict. And the reason for that, well, there's two reasons. One is the data itself. Engineers already know and what they want to track, things like lap time deltas, gas rate changes, or yield percentages. And these things make great training targets for models that we would create together. And it's also about interpretability. With these models, we know exactly what goes in and what comes out. We're still using machine learning to form nonlinear relationships between inputs and outputs, but we are in control of the data we put into it, how we select it, and how we use it, and ultimately what we're trying to predict or estimate. So imagine you're in a Formula One team and you're in a race strategy team, and you're really interested in how you can predict the optimal pit stop to make during a race in real time. To do this with AI, you wouldn't just throw all the past race data at it. You would define the outcome you care about, You would build logic to compare strategy outcomes fairly, and you'd ultimately need to clean, align, and structure the data around race dynamics to be able to distinguish between raw performance and compromised performance during a race. So most of the engineering work isn't in training a model and going through tuning a model, it's in actually engineering the right solution. And building something that can actually run in a real-time environment is another challenge on top of just being able to, I guess, train and formulate a model. So this really isn't about just applying AI and machine learning generally. It's about being able to look at the systems we're running and how we can use it to go from monitoring our systems to actually understanding what they're telling us so that we can be informed to make smarter decisions, ultimately as fast as possible. And suddenly engineers they're not doing things manually. They're not manually watching for the same issues in their trends. They've got models for that now. And they can start working on these projects to automate repetitive, time-consuming interpretation tasks. And that shift, it really does enable more strategic system-wide thinking across an engineering team. And not just across one sort of engineering discipline, but actually across multidisciplinary teams as well. At SIG Machine Learning, we really specialize in helping engineering teams scope and deliver AI projects for different use cases that are relevant to their operation. This could be applying AI and machine learning for enhanced signal processing that is applied to exception-based monitoring, asset performance, predictive maintenance, advanced process control, or strategic planning in that example there in the Formula One race strategy. We're really looking at helping you uncover where efficiency can be gained, risk can be reduced, and performance can be improved, all at the same time as helping engineers work faster and smarter. So whenever your machines are going to be telling you something through sensor data, you'll know how to listen. You'll know the language they're speaking to you in, and you'll know how to speak back. And this is really all about the application of AI to inform more enhanced signal processing capabilities. So if you're exploring AI and machine learning and how it can support you in your operation, we're more than happy to catch up and talk to you. So please feel free to book a discovery call with us, with me and our team, and we can explore use cases, just have a conversation, and also show you a demo of our platform as well to show you what it looks like in practice. So speak soon, and bye for now.